Good morning, everyone. It's really a pleasure to be here at SharkFest. Still have many friends in this community, and the feel of the conference has not changed since the last time I presented and I participated to this conference. Still, great, really like a family. So thank you for having me here. When you use Wireshark, your experience is sort of something like this, right? You have a beautiful dashboard in front of you. You are in control, you steer where you need to steer. Just great, right? Today, during this next, like 45 minutes to an hour, we're going to do something that is a little bit more like this. So I'm going to spend time. I thought it would be fun to essentially look at how things work under the hood, especially in those components that Wireshark and other tools use essentially to capture the packets and to collect essentially the information that they dissect and decode, and do it in a way that essentially sort of tells a little bit the story of how essentially I contributed a little bit to this and participated to this effort. My name is Degioanni. Currently, I am the founder and CTO of a company called SysDig. The name of the company comes from the open source tool SysDig, which is the one that Gerald was mentioning before. I've been involved in packets, networks, and open source essentially my whole career, starting in 1998, 1999 when I was in school, then during my PhD, then during Case Technologies, which is the company that was originally behind Wireshark and that I founded together with Gerald and other people. And so I'm one of the old guys here that have seen quite a bit of things. The title of my presentation, of my keynote, is a brief annotated history of capture. I will do it in 4 chapters. I will talk first of all about capture, then about filtering. I will spend a little bit of time on how filtering, or at least the kind of filtering that was initiated by TCP dump and Wireshark, is evolving, in particular with facilities like EBPF in the Linux kernel. And then I'm going to talk a little bit about capture, but capture for system calls, which is what essentially SysDig does, and to give you an idea essentially on how the same technologies can be leveraged and used to do different things than just capturing packets, even if they were born and specifically designed originally to capture packets. So there's quite a bit. So let's start from capture. You will notice some of these slides have funny, bright colors. It's because I actually went back and I got like these are from presentations that I did during like my graduation thesis in 2000, right? So these were actually created with PowerPoint and with the color schemes of PowerPoint almost 20 years ago. But this gives a little bit of the historical feel as well. So from the very high level, capturing packets and using a tool like Wireshark can be described with a few high-level components. Of course, there's a network and there's a network adapter that is interfaced to the network and receives the packets. Then there's an acquisition system. Acquisition system is a component that needs to talk somehow to the network adapter to actually get the data out of the network. And then as a component that essentially organizes stuff for the applications that are sitting on top of it, let's call it capture driver. All of these typically runs in the operating system. Then there's an application that typically, there's a capture library, one or more capture libraries. Then there's some kind of processing, and then there's a front end, right? A user interface, like the Wireshark 3-pane view to see the packets, but can be anything else, right? So this is basic architecture. When we talk about this kind of stuff, The seminal paper, the Bible for this, is the 1993 paper about BPF, about packet capture in the BSD kernel, written by Steve McCann, which incidentally is also the founder of Riverbed, the sponsor of this conference, and by Van Jacobson here at Berkeley. So there's, you know, a lot of connections here. And this is really like, I still remember like the single chapters of this paper. I recommend everybody that is interested in this kind of stuff to just go and download it. It's technical, but not too technical. It's very well written. And essentially, this paper describes for the first time packet capture. You know, what we do now every day when we use Wireshark didn't exist before this and was essentially invented architecturally by these guys in 1992 and 1993 and was described in this paper. A whole industry of a whole, you know, community of researchers like me. Essentially, I started my career reading this paper, you know, and it's like, oh, okay, you know, that's how you build something like this. The architecture described in the paper is like summarized in this slide. So from the bottom, there are packets coming to the network. There's typically a NIC driver, a network interface card driver. And what Steve McCann and Van Jacobson did was they sort of, since you know the BSD kernel is open source, they did a modification called network tap into the network card driver to essentially being able to get a different stream of the packets. Typically, the network card would just, the driver would just send the packets up to the protocol stacks. And the network tap was their way to essentially get a hook into the network packets. At that point, there was, there still is, you know, it still works this way. There is a filter. We'll talk extensively about the filter later, but essentially, it's like what you still use when you create a capture filter in Wireshark or in TCP dump, right? It's the same syntax, it's the same thing. And there was essentially an evaluation of this filter in the kernel of the operating system, and there's an attempt to do that as soon as possible, because especially if the filter is selective, you can save essentially a lot of resources by dropping the packets before you even copy them into a buffer. The filter is essentially a Boolean expression that says yes or no, and if the answer is yes, the packet goes into a buffer. The BPF architecture was based on a dual buffer, so there's an accumulation buffer that the network card fills after the filter accepts the packets, and then there's a buffer that the application consumes to bring the packets to user level. When the accumulation buffer is full and the application buffer is empty, they get switched and things start again. There's a further copy at that point, and this is where essentially the transition between the kernel of the operating system and the user level applications and other space happens. So at that point, the packets go into the memory of the application. There's a library which probably many of you are familiar with, which is called LibPickup, which is essentially the standard library that every application that captures network packets, including Wireshark, links and uses essentially to get the packets. LibPickup gives a nice abstraction, does several things, and we'll talk a little bit about it later, but some of the important things that LibPickup does is implement an easier abstraction to talk to any, essentially, a packet capture system, so pickup open, pickup next, and so on. Support for trace files. Even if with Wireshark things are a little bit more complex because Wireshark does not use libpickup for trace files. It actually implements its own loaders for trace files, but libpickup essentially is able to abstract in a pretty nice way capturing on live packets versus reading packets from a file. And then, of course, libpickup is all the interface to make it easy for you to create the filters and inject them in the kernel driver. Typically, when you're talking to something running in the kernel, in particular a driver, you need to use interfaces like I/O controls or system calls and the kind of stuff, and that interface is not very friendly, and so lib pickup just gives you some easy functions to do that. All right. Fast forward to I think this paper was 2000, if I remember well, and this is actually a paper in which me and my advisor at Politecnico di Torino in Italy described Win Pickup, which was the very first packet capture library for Windows. At that point, well, that's when actually, we started seeing that there were open source tools for packet capture, but they were only working for Unix operating systems. And the way I started getting involved with this community is I was at my last year of university in Italy, and in order to complete my university, I had to do a project, and I was very much into networking and network packets, and so I went and asked the computer networks professor if he had a project for me. And at that point, he taught something that I strongly agree with, which is the best way to learn networks is to observe networks, which now is trivial. Now everybody can go and in a second download a tool like Wireshark, and immediately, of course, in 30 minutes with Wireshark, you learn like as much as following, like maybe a 10-hour class, on computer networks. At the time, there were only commercial network analyzers. The vast majority of them were just based on hardware boxes, that were tens of thousands of dollars or more, And my professor wanted every student to have access to a network analyzer, and we had Windows in the lab, So it's like, okay, we need to build a network analyzer for Windows because there's no way I can afford buying even a single one, for the students. But I want the students to have it. Looked around, yeah, you can, get something for Solaris. Linux was very young now, but yeah, Ethereal started for Solaris, for SunOS, right? But again, those were expensive workstations, and we needed Windows, we needed regular PC. So started working, initially the goal was just working on a port, and we actually started working on a network analyzer called Analyzer, which again, probably no one remembers here. But at that point, it was, like Ethereal and Analyzer were the two tools that somebody would use. Analyzer was Windows only, and Gerald was much better at essentially running a community. So at a certain point, it was like, forget about that. We focus on the packet capture, which is what we do well and we really need, and the port, to Windows, which is what we need for the lab. And let's just use Ethereal, which at this point it was started becoming much better. But in order to do this, we had to essentially build the equivalent of BPF, which was described in the previous paper for Windows, right? So started working on that and came up with an architecture that was heavily inspired, but slightly different. So let me focus on the differences here. First of all, the network tab now is not in the NIC driver because, of course, you don't have access to the source code of the NIC card driver in Windows, right? So we actually decided to use a facility, a stack into the Windows kernel called NDs, which stands for Network Driver Interface Specification, and just hook at the level of being like a protocol. So instead of being an alternative to the protocols, we were just another protocol sitting essentially near TCP, the TCP IP stack. The filter is the same, and we made a point on supporting essentially the same filter in virtual machine. We implemented a circular buffer instead of just a dual buffer, and we tried to essentially play with the size of this buffer to give essentially a bit more room to the packets, for the packets to be captured. And at user level, we created a library that was essentially a lower level library that would talk specifically to Windows, and we tried to keep lib pickup as similar as possible to the Unix version so that there could be a single code base. So essentially, our goal was like, we would like lib pickup to be used in a way that is as similar as possible on Windows, and we don't want to change it with a lot of Windows-specific stuff, so let's build another DLL that sits underneath it, and pick up a Windows with just call it. And that's the WinPickup implementation in 1999. This worked pretty nicely, and I remember talking to Gerald around those times, and it was, first of all, for me, mind-blowing, because I was just building this kind of thing to make, like packet capture work in our labs, and by the end of my, when I got my degree, there were like 100,000 downloads of this thing, from people around the world. It's like, I didn't even know who downloads it, But it's because, like, tools like Ethereal noticed that finally there was, a lib pickup for Windows, and they could easily, essentially, be ported to Windows, and that gave a big boost to WinPickup, but to Ethereal as well, and made, like, it was like a nice way to have a win-win situation where we could support each other and get more visibility for each tool. That's how communities work well, by the way. So at that point, if we explode a little bit the WinPickup architecture, we can see that, there's a little bit of buffering already by the network card. Essentially, there's a PCI transfer, and the packets are moved to memory. Then there's a filter, there's timestamping, and there's scoping. All of this happens in a function called tap, which works in the context. Let's call it interrupt context. It works in the context of the NIC driver, right? It's much more complicated than that, because you cannot really do all this stuff in an interrupt. But it's like when a packet arrives, typically the network card gives you an interrupt to tell the CPU, okay, there's data for you. And then as a consequence of that, there's this processing of filtering, timestamping, and putting essentially the packets in a buffer. Then there's a function called read inside the WinPickup driver, which is in application context, right? So here you come from the read, you come essentially from the context and header space of the application, and this read is called essentially when the application requests more packets, and it's initiated by the application, and essentially what it does is it mainly copies the data to the memory of the application itself. Of course, I started having a lot of fun with this, and so I decided to keep working on this after I got my degree. And at the point, it was like, okay, this works, but it's slow, And networks were becoming faster and faster. At that point, it's when we were going quickly from 10 megabits to 100 megabits to gigabit, in few years. So the same tool that was very useful at slower rates was becoming completely useless at higher rates, right? So this is actually coming again from my thesis, from my PhD thesis. Started to focus on, okay, how can we make this better? How can we optimize it, right? And I'm not going through all of these in this presentation. I don't have time, but it's just to show you how we try to methodically, essentially try to understand where were the bottlenecks and make this better, including profiling. And again, all the Excel charts, but I think they're still interesting because they show before optimizing, you always need to measure. That's why what we do on the network as well, right? Ideally. And even here, without going through the different numbers, but by measuring essentially how much capturing a packet was taking, you can see that there's quite a bit of time that is just spent, by the NIC driver to just bring the packet in. But then one thing that, for example, was interesting is timestamping was taking a lot of time because you have to call a kernel function to get the time, every time a packet arrives, and you can have many packets that are coming. Like timestamping was even more substantial than filtering, in terms of overhead. This was a filter with 21 instructions, so a relatively simple filter. So filtering can become, a big part if filters are complex. But in a normal filter, like a TCP port or something like that, filtering was pretty small. So we went methodically and we started shaving time for all of these components. And as you can see, we went to a situation where pretty much almost the majority of the time was just at this point NIC driver time. We optimized timestamping by just calling RDTSC, which is a native CPU instruction, instead of asking the kernel for the time. We optimized the filter, which was a very fun project, by writing a just-in-time compiler for the BPF in the kernel. This was 15 years before people started thinking again about just-in-time compiling BPF. We'll talk about that later. And we essentially managed to sort of double, the performance of capturing packets in the Windows kernel. And this, I remember, I was very proud of that at that point. This is, again, around 2002 when I did this profiling. Linux at that point was, relatively early, but it sucked, capturing packets. And I was pretty proud that we were substantially better, in terms of packets captured than even the BSD kernel, which was, my gods were only doing 34%, I was doing 68.
I remember you making a lot of people on Slashdot very angry.
Yeah, exactly. Yeah. At that point, it was like, okay, there's only so far you can push an architecture like the one I described you, And even with all of these optimizations, the architecture that we had in place was still very much BPF, just very carefully optimized BPF, right? So around those years, I also started thinking, okay, what else can you do that is better? And one of the things that you can do is doing some processing in the kernel. For example, many of us very often just need to capture packets to get high-level statistics, like how many HTTP packets am I seeing on the network, or are there retransmissions, So these are relatively simple things to do, especially when they're stateless, especially when you don't need to keep state and you can do stuff at the port level, at the layer 3 and stuff like that. So one of the prototypes that we built was an engine that would completely reside in the kernel and would do essentially put together filtering and counting, so that you could easily express, like a BPF filter, like a port 80, and then this would give you like the bytes and the number of packets for the specific filter. Another thing that I worked at the time, which I wouldn't do it again, but I think it was interesting as an idea, was shortcutting. Again, many times what we do with packets is just saving them to disk. We don't need to do anything else, And that's not really CPU bound, it's IO bound, but at the same time, in the traditional architecture, when you're using like TCP down -W, you are, copying packets multiple times because they go to the capture driver, which copies them to the application under space, where you are writing them, and typically libc as a buffer, and then this buffer gets copied in the kernel, and then from there they go to the disk, right? So what about just connecting things and very quickly just mapping essentially the packets that are coming from the network card and doing direct I/O with those packets, essentially with sending them to the driver that implements, the file system or even the storage, And again, that can save a lot of time for the specific use case. It's also something that is pretty dangerous to do because it's not trivial to do. That's why I was saying I wouldn't do it anymore today, but we'll talk about later maybe how I would do it today. And at that point, as you can see, the NIC driver is the vast majority, right? Because what I'm doing for something, especially for something like this, I'm just filtering and counting, right? Which are both pretty lightweight, especially if I just-in-time compile the filters. And at that point, with this, you reach the limit of what you can do with a normal network card on a normal operating system. So what do you do at that point? You use something that is specifically designed for packet capture, right? And there are many of these, and this is the time, let's say early 2000s, is when commercial companies started, like Endace, Napatech, and so on, started selling cards that were specifically designed for packet capture. And of course, at this point, architecturally, you can get substantial improvements, because first of all, the capture card has an FPGA or something similar, but computing capabilities on board and memory on board. So you can buffer packets much more than a regular NIC driver, and you can do timestamping. You remember how heavy it was, but also it can be much more precise if you do it in an FPGA when the packets just arrive. Because when you do timestamping in an architecture like the one I described before, the packets have already been buffered by the NIC driver before you receive them. So the timestamps can be pretty inaccurate. While if you do that, in hardware, they are much more accurate. You do buffering, and then you do batched, optimized copy into a ring buffer when you have to transfer the data. So a normal NIC card sends every single packet to as a different PCI transfer, and as I was saying before, gives you an interrupt after that. That's not true in practice because even the normal Intel NIC tries to batch the interrupts, but you still receive enough interrupts that slow everything down. Well, a capture card would never give you an interrupt. It will just write to a buffer, which is conveniently mapped not in the kernel space, but in the memory space of the application. So it just goes directly into the application address space. And then the network card just gives you essentially an address, an IO value that you can go read to understand where the network card is in the buffer, and one that you can write to tell the network card where you are. So essentially then it's an easy, like a standard circular buffer. So at that point, there's essentially no transitions between user level and kernel level, and you just advance, your tail while the network card advances its head, and everything is very, very efficient. This works very well, and at that point, with an architecture like this, the network card would not be the bottleneck anymore. So if we go to the previous slides, this would be pretty much completely removed, right? So that's when things become fun, because there's, again, space to optimize in software, right? So one other paper that I published, this one is in 2004, was the first attempt to, now you have a bunch of packets that are coming very efficiently to memory, and you start having the first machines that are multi-CPU, multi-core, multi-thread, right? At that point, you can start playing with putting a scheduler on top of this buffer and sending this data to multiple threads, either in simple and trivial ways, like just sending the packets randomly to the different threads if you want to do like basic counting, or maybe a little bit more sophisticated, like the multiplexing by port, or very sophisticated, like doing it by tuple, so that you have consistency essentially, and you know that a thread always receives all of the packets for a specific connection. There's been substantial work there. I'm not going through all of that work, but that paper was one of the papers that I'm the most proud of, because we were really the first ones trying to work on this kind of stuff. And we were able essentially to, for the first time, to support 10 gig packet capture on a normal PC, that you could buy at Fry's or wherever. And that was 10 gig at that point. Now it's nothing, but at that point it was a lot, So it was like no one could believe us when we were telling we could do it. One other thing that I had a lot of fun building is, now the problem is you can buy one of these network cards. They're very expensive, right? At the same time, machines are becoming more and more, like parallel and multi-core and multiple CPUs. So I started thinking, can you take a machine that maybe has 32 CPUs, and just take one away from the machine to simulate in software with one CPU and network card. And essentially, that's what I built. And the way it works is the NIC is still a small buffer, but you have a CPU that is polling 100%. So when you're using this kind of architecture, you will see one of your CPUs always at 100%, because it's always reading the registers of the network card to see if a new packet has traversed the PCI buffer. So that means there's no interrupts, but the CPU is always spinning constantly, 100%, which means that as soon as a packet arrives, you know it right away. A few instructions later, you know that the packet is there. So super precise timestamping. And then what you do is, since you're always polling, you constantly reorganize the descriptors of the network card in hardware to simulate a circular buffer. So you already position the packets as they arrive in a way that simulates what a commercial network card does, by essentially tricking the network card in constantly making it, going it around. And then you do what the network cards do. You map everything into the application, so you have minimal copies as well. The network card will just, the Intel card will just copy the packets in the address space of the application. So drawbacks is you have to give up a CPU. Benefits is this is really fast, it's really precise, and I could get pretty much almost the same speeds of a network card. So this eventually became a product, a derivative called TurboCap, a case and derivative. It's discontinued now, but it was funny because it was a way for us to essentially being able to sell a network card for a fraction of the price because it was just essentially normal Intel card with all of this trickery in software. And yeah, it was just super fun to build. All right, let's go to filtering. We need to start going faster. Okay, filtering. Filtering, first of all, caveat here means capture files, right? Back to the paper, because the original BPF paper describes this pretty well. But there's another paper that the same authors published a few years later. I think it's like 2000 or 2001. This one is BPF Plus, which was like version 2 of their BPF, written by the same group here at Berkeley. But it's BPF Plus kept closed source, so it was a little bit like a failed project. But the paper is still very interesting because it goes more in deep into how the filtering system in BPF works and how especially the optimizer, the compiler and the optimizer work. So just worth mentioning here. So how does that work? The filtering architecture of something like BPF and so Wireshark works from, you write a filter in a language, port 80 is an example of a filter, goes to a front end, which compiles the filter and transforms it into an intermediate representation. The intermediate representation goes through an optimizer and generates bytecode, essentially. So code for a CPU, essentially. And up to this point, this is very similar. I mean, this is a diagram of GCC, of a compiler, of Microsoft Visual C. What is different is that then, this code goes into the kernel of the operating system, is checked for safety, and then it's either interpreted or just compiled for every packet, essentially. In terms of intermediate representation, there are two ways that typically you can express something like a Wireshark capture filter. One is the Boolean expression tree. So here, every node is a Boolean operator, and the leaves are checks. This is how I would build, and how I have built, because I've built multiple, packet filters, and typically how I build it is the easy way. It's a less sophisticated way. It's slightly less efficient because it can be redundant, but it's very easy to implement because either in a high-level language like C or with a stack machine. The BPF guys were smart, way smarter than me, so they picked a different representation, which is a direct acyclic graph. It's essentially a graph that goes only in one direction. And a DAG, direct acyclic graph, is little bit more complex as a representation, but it works much better when you want to run an optimizer on top of that, because it gives you more optimization opportunities by essentially playing with the branches and with the nodes, and also fits better a register machine, which is what they implemented in BPF. So in terms of optimization, the way it works is the compiler generates a graph like this, and then the optimizer takes this graph and starts playing with the graph to see where there are redundancies in the nodes or in the connections, and creates something that essentially is faster and is more efficient. The result is code for virtual machines. So the BPF filter that I was describing in the diagrams before is actually a virtual machine with a pretty simple opcode, which is always the same, pretty simple instruction format, which is the same, and a simple, but as you can see, pretty complete instruction set. So your filters, like port 80, actually get translated, first get optimized, and they get translated in code that runs in a virtual processor in the kernel. Talking about these, my favorite TCP dump flags. Who knows what these flags do in TCP dump? Other than Gerald. These essentially allow you to see what TCP dump produces in terms of filters. So if I do something like a TCP dump -d, it essentially shows me the instruction. There's no filter, right? So this instruction just says, return the whole packet ever, right? But if I do something like, I don't know, IP, I start seeing, okay, this loads address 12, which is a protocol type of Ethernet, compares it to 800, and then depending on the result, either keeps the packets or drops the packet. So it's super fun to just go and play and type your filters and see, of course this is simple, but I don't know, let's do HTTP port, right? And you can see more complex ones, right? And then, even more fun, capital O will show you the unoptimized filter. So if I do the same thing, but with capital O, I will see a longer filter because it shows me essentially what happens pre-optimizer. So I can even, inspect and see what the optimizer does with me when I type, an arbitrary filter. So highly recommend you to play with it. It's just fun to see, the internals exposed to you. And dash DD, for example, actually gives me the C code that I can just embed. If I don't want to use pickup, I can embed this into a program, ship it down to the packet capture driver, and this is actually the binary that it will execute. One more component that is interesting to talk about is the verifier. So the problem is there's actually a VM in the kernel of the operating system that is running arbitrary code. So you need to make sure that this VM doesn't crash your machine or doesn't freeze your machine, for example, by doing a loop that never returns, right? So there are a set of conditions that are checked by a verifier that is actually sitting in the capture driver and rejects a driver that doesn't meet specific condition. For example, in the original BPF, you can only have forward jumps to avoid this loop problem that could freeze the operating system. Verifier is almost as complex, as the filter compiler, and it's something that actually runs in the kernel of the operating system, and every filter is checked by that before it's executed. All right, BPF in a general way is super fun. I mean, just the idea of having like a virtual machine there just to check if your packets are TCP packets has always been so fascinating to me, From one point of view, you can see it a little bit like over-engineering. From the other point of view, it's like, God, this is fun, So eBPF is even more fun. There's been a lot of work on filtering in the Linux community, especially in the recent years. So eBPF stands for Extended Berkeley Packet Filter, and is based on the same concept, but is a dramatic extension and evolution of the same concept. And as you can see, it's been gradually introduced in the Linux kernel relatively recently, and it's become useful, let's say, from version 0.7, 4.8 of the Linux kernel. So let's say it's been around and useful for, let's say, 5 years, something like that, ballpark, more or less, And what's different in eBPF? The instruction set is more advanced. There's much more stuff that it can do. It can run sub-programs, so it's not just, like a linear little program, but it can have subroutines. It can call places in the kernel to do stuff, like to get a data structure. BPF was strictly just executing instructions that were looking at packets. While with eBPF, you can go and tell the Linux kernel, okay, drop this packet, for example. Or you can tell the Linux kernel, or you can ask the Linux kernel, okay, what's, whatever, the user application connected to this packet. So there's stuff that you can call in the kernel to get more information or to do actions. There's the concept of maps, which are essentially tables, lookup tables, that are part essentially of the instruction set. There's the ability to do backward jumps with limits. So instead of just denying doing loops, you can do loops, but they have to be like less than 4,096 instructions. For that reason, for all of these reasons, the verifier is much more complicated because the virtual processor is more sophisticated, and what it can do is much more complete. There's a very efficient just-in-time compiler. You can attach it to way more places inside the Linux kernel, and there's actually a new system call in Linux just to control this. So architecturally, eBPF works in a way that is similar. You write code, you have a compiler, there's a verifier in the kernel, there's a virtual machine that is connected to all of these different esoteric places in the kernel. So you can essentially plug it into something that is much more than packet captures. And then typically, you can return results to the user either directly with a mechanism similar to what I described before by sharing a buffer with data, or through maps, which are a facility just offered by the virtual machine that makes it very easy for you to just share tables or values with the user level. What's really interesting with eBPF is that the community really did a lot of work at the front-end level. So there's this set of tools called BCC, which essentially, so what people have done is, instead of with all of the whole architecture that I just described, you have a simple filter language and a specific compiler that generates pseudocode. What these guys have done is they just made a C compiler, LLVM, be compatible with the BPF virtual processor, so that you can really write a C program that gets compiled and becomes a BPF program. And then you have essentially a Python or JavaScript or Lua wrappers that you can use essentially to inject these programs in arbitrary places in the kernel. So instead of using lib pickup, you can really have your C program running in the kernel talk to your Python program running at user space, so that easily from Python you can create statistics or create user interfaces or something like that. Again, can you imagine? We went from what I described before to now being able to really write an arbitrary C program with functions and subroutines and libraries and whatnot, and get it compiled and get it in the kernel. So and it's extremely efficient at the same point, So with this, of course, you can do what I described in the previous, 30, 40 minutes, but you can also do more, like, for example, you can hook, you can put a BPF program at the network, before the network stack and after the network stack. This is, for example, what tools like Cilium do. There's quite a lot of networking now that is done in kernel just using BPF, sophisticated stuff like filtering, like, DNS support, all of this kind of stuff. So not trivial stuff like just accepting or rejecting a packet. Or stuff that is completely, outside the network, like you can use eBPF, you can connect it to the stuff like the Linux security modules, like SC Linux, for example, and you can run eBPF programs connected to like SC Linux stuff or trace points or anything else that you want to do in the kernel. If you want to learn more about this, Brendan Gregg is the most visible face behind eBPF and everything that is happening nowadays with Linux tracing, which is a lot. Is a little bit like the Gerald Combs of Linux, modern Linux tracing. So this page has quite a little bit of material. One more section about what I'm doing currently with sysdig. So let me start with why I love packets. So packets have properties that are really nice. They're information rich, they see everything, they can be collected with minimal overhead, they don't require invasive instrumentation, and they are, for that reason, they can be used by many important tools, right? With packets, you can do application monitoring, you can do runtime security, you can do troubleshooting, you can do intrusion detection, you can do forensics, you name it, And all of these are huge industries, right? That's because of, the ability with packets to see what's happening deep if you decode them into what an application is doing in a way that is very transparent and doesn't require intent, doesn't require you to go and change this application to get the observability, right? Only problem, capturing packets becomes harder and harder, especially where's the spam port, where's your wire when you're running instances like in the cloud, on AWS, and so on, right? So when I started SysDig, the idea was like, how do I support these workflows that I contributed creating in the cloud, and how do I make it possible for people to do troubleshooting, visibility, and so on, in a place where getting packets can be challenging, right? And so I started exploring, essentially, hooking into system calls and treating them the same way as packets. All right, so the last 4 slides give you the elegant rationale for why I started my current company, SysDig. In practice, let me tell you a secret. Don't tell my investors or my customers, but the reason why I started is because I wanted to build another capture driver. And so, if we look at the architecture of something like SysDig, you immediately recognize something very similar, even without having to describe you every single component. The difference is that instead of getting packets now, SysDig gets system calls through a kernel facility called tracepoints, which allows you essentially to go and hook into a function in the kernel, and this function in particular is sysenter and sysexit, which is the function in the kernel that receives the system call and the one that returns from the system call. And then, there's a capture driver, there's a buffer, which is mapped with user level. There's a capture library, which implements trace file support. By the way, the trace file is the pickup-ng one. So I decided to use the same file, and that is a testament to the versatility of pickup-ng, because it absolutely used to just store system calls in blocks by SysDig. And then where things get a little bit more interesting, and we'll talk a little bit in a few minutes, is what happens on top of that. Architecturally, a couple of things that are worth noticing in the SysDig architecture compared to the BPF one and the WinPickup one that I described before. First of all, I decided to go with the memory map right away. So one of the benefits is there's no need for filtering at all in the kernel of the operating system, because the packets are just mapped, and the driver is really tiny, really as small as possible. It just takes the system calls and put them in the share buffer, and everything else happens at user level, which not only makes the architecture very efficient, but you also don't have to writing kernel code is much harder. You need verifiers because you cannot crash in the kernel. So making having the share buffer allowed, for example, to only have filtering at user level without having to have 2 different virtual machines, one to filter packets from file and one to filter packets from the network. What makes it more complicated is we're dealing with system calls here and not with packets. So with packets, you have stuff coming only from one entity, the network card, right? So you don't need essentially synchronization at the input level in the kernel buffer. You only need it at exit if you have multiple consumers, right? While here, there are multiple applications that are generating system call, and they all go into the buffer, right? So the problem of something like that is it requires synchronization. You need a mutex or a spin lock or something like that, because otherwise you can have 2 writers that put data in the buffer at the same time. I wanted to avoid that because, of course, synchronizing is slow. And again, you can have million system calls every second, right? So the way I implemented it is there's one buffer per CPU. So like this is a diagram of SysDig running on a 4 CPU machine. Every CPU has its own buffer, And these buffers, the way you write to these buffers is you disable preemption of the CPU for the brief amount of time in which you're moving data to the buffer. And by disabling preemption, you know that no other thread in that CPU will interrupt you. Disable preemption in the Linux kernel is just a matter of changing a value, so it's just a memory write. It's very efficient. And somebody else could, when you disable preemption, you do only per CPU, so somebody else could run, but it will be on a different CPU, and it will own it completely, right? So by having multiple buffers and disabling preemption, the architecture can essentially be completely lockless and be super efficient without any need of synchronization at the right level. And then that adds a little bit of complexity because at the lib pickup level, you need to put everything together again. And so there's a little bit of CPU time that is used for that. One thing that sysdig does is it really treats system call like packets. So imagine a system call like open, that has a file name and flags. It gets converted into, fields like the PID of the process, the event type, which is open, number of arguments, and then the arguments, packetized. So that's very fascinating because at the point you can do what you do in Wireshark. You can have display fields, on top of that. And you can also have filters on top of that. The thing that makes it a little bit more complicated is state is not always contained into the events that you collect. For example, if you just see a write, you will see a file descriptor, which is a number, right? But I don't care about the number. I care about the file, right? So what sysdig does is there's an open. If there's a write, there was an open before, right? So sysdig sees the open and keeps track of the fact that the open, which gave me, file descriptor number 3, correspond to a file called myfile.txt. So sysdig keeps at a user level sort of a mirror of the file descriptor and process tables of the operating system so that it can offer essentially functionality like filtering that is meaningful and in context. I can create a filter on a process name and on a file name or on a connection or something like that. So the beauty, for example, with sysdig, since it's operated at the system call level, I can do something like sysdig fd port equal 80 and proc.name different from Apache, and they will see all of the port 80 traffic that is not generated by Apache. So there's the connection between the process and the network data. Only problem is what happens, because sometimes when you start capturing, you will see reads and writes for connections that have already been established, for files that have already been opened, right? So you won't have the metadata for those. So to solve that problem, when sysdig starts, it does a scan of proc to create an initial version of the operating system mirror, and then after that, it will just use the system calls to keep this state up to date. So every file descriptor, every process, even if they were not, if they were created or opened before sysdig started, you can still use them in filters. One thing that we've done, like last year, Gianluca Porello actually did it, another guy coming from Case, is we rewrote completely our driver, which was a kernel module, originally, as an EBPF program. So we go back to EBPF and how powerful it is. Originally we were using BPF to create like 10, 20 instructions from packet filters. We were able to create a 6,000-line C program that can be injected in the kernel, and there's the full functionality that I just described to be able to do like these multiple ring buffers and all of the collection and packetizations that system calls, all of this kind of stuff, all completely in eBPF so that you can inject it in the kernel in a completely safe way without to compile a kernel module. This supports containers, so one nice way of deploying sysdig is you just run a container on the machine. Sysdig detects the version of the operating system, deploys the capture driver or the eBPF kernel module, and then it's able to to look into namespaces and see groups, so that all of the system calls that are captured, you can see the ones that are generated by containers as well, which is very nice because doing troubleshooting of containers can be challenging. And the other thing that it does is it talks to the orchestrator to make it possible to do things on a service-by-service level. So this diagram shows a bunch of machines on the left side and containers running on these machines. And if you're using something modern like Kubernetes or stuff like that, essentially you will have the orchestrator that deploys your services on arbitrary machines. This color coding here is the type of service, right? So green could be credit card validation if you're a bank, and blue could be, I don't know, your login, your user login. And these, sit on the same machines. But when you're looking at data for these things, you don't want to look at it like on the left side. You want to see, the average response time for the yellow service, And in order to do that, sysdig essentially talks to an orchestrator like Kubernetes or like Mesos and understands the color of these entities and puts things together in a way that allow you to ask questions like, show me only the packets that containers for service A are sending to containers for service B. And sysdig will find, the service A containers and the service B containers, and will show you only the traffic. And there's quite a little bit of work that goes under the hood to be able to implement that kind of stuff. All right, it's 9. I'm done. There's many things that I couldn't cover here. Maybe next time I come, but trace file formats is very interesting. PF ring by Luca Deri. MPCAP, the new version of WinPickup written by the mmap team, very interesting to look. Wireless capture, dynamic code instrumentation. If you're interested in this kind of stuff, I recommend to go take a look. Otherwise, again, maybe next SharkFest. I just want to close in another 30 seconds just to prove that I was actually there. This is, I think, the first picture that I have of Gerald in our case office. I don't know if you can see it, but we were working on wireless capture at that point. So yeah, this very sophisticated handmade wireless antenna setup. This is Gerald on stage at SharkFest, first SharkFest, 2008, Janice was there. So this is the first ever keynote at SharkFest, 12 or 13 years ago. This is actually Janice working on organizing SharkFest #1, And I never worked. Exactly. So I close with Janice because I want to thank Janice for inviting me here. Hopefully this was interesting for you. It definitely was not only fun, but an honor for me to come back to, to present in front of you. So thank you very much for your time, and have a great rest of your conference.